60 kilometers. That is the distance between yesterday's magnitude 6.2 earthquake and the exact spot where one of the most violent strike-slip ruptures in the last 25 years tore the ocean floor apart. 60 kilometers. That is 37 miles. And here is what you need to understand before anything else. The earthquake that struck that same fault in 2013 did not start as a magnitude 7.8. It started as a magnitude 6.1. Then 4 days later, a 6.8 hit, and then 30 hours after that, the fault exploded with a 7.8 that shook the entire southern ocean floor and sent seismic waves racing around the planet. Now look at what happened on this same boundary on August 22nd, 2026. A magnitude 5.7 hit first. Then 7 hours and 42 minutes later, a magnitude 6.2 struck the same region. The escalation pattern, the location, the fault type, the depth, and the distance from the 2013 catastrophic rupture are all pointing to one thing that nobody in the mainstream media has said out loud yet. This boundary is active right now. It has a proven history of producing earthquakes approaching magnitude 8. And the question that every seismologist watching this plate is quietly asking is the same one you should be asking after watching this. Was yesterday just the beginning? Let us start with the exact details of what happened, because every single number here matters and they all tell the same story. A strong and shallow earthquake registered by the USGS as magnitude 6.2 hit the Scotia Sea at 0822 UTC on August 22nd, 2026. The USGS reported a depth of 10 kilometers, which is 6.2 miles. EMSC, the European Seismic Monitoring Agency, reported the same magnitude and depth independently. The epicenter coordinates are 60.379 degrees south, 47,605 degrees west, 10 kilometers deep. When seismologists see 10 kilometers as an initial depth assignment, it typically means the earthquake is shallow and the exact depth is being refined. The reviewed moment tensor, the scientific reconstruction of exactly how the ground moved, gave a depth of about 11.5 kilometers. That is still extraordinarily shallow. And shallow is the word that matters most in this story because shallow, strike-slip earthquakes on this specific fault system are exactly the type that have produced the largest and most violent seismic events in the Southern Ocean in living memory. The epicenter was located 1,230 kilometers, which is 827 miles, east-southeast of Tolhuin in Tierra del Fuego, Argentina. It was 1,368 kilometers, or 850 miles, east-southeast of Ushuaia, which is the world's southernmost city. Put that geography in your mind for a moment. You're looking at a point in the ocean that sits in the deep south between the bottom tip of South America and the frozen continent of Antarctica. There is almost nothing out there. No shipping lanes, no cities, no coast within hundreds of miles. Just ocean, ice, remote islands, and one of the most geologically violent tectonic boundaries on the face of the Earth. Now, let us talk about what fault this earthquake actually happened on, because without understanding the South Scotia Ridge, you cannot understand why yesterday's event matters. The South Scotia Ridge is the plate boundary between the Scotia Plate and the Antarctic Plate. It runs roughly east to west across the southern Scotia Sea. The South Scotia Ridge is a left lateral transform boundary between the Scotia and Antarctica plates that is sliding at a rate of roughly 11 millimeters per year. Left lateral means that if you are standing on one side of this fault and looking across it, the ground on the opposite side appears to be moving to your left. This is pure horizontal sliding motion. The two sides of this boundary are not colliding into each other and building mountains. They are not pulling apart and creating new ocean crust. They are grinding past each other sideways at 11 millimeters per year after year, decade after decade, century after century. 11 millimeters per year sounds harmless. It is less than half an inch per year. But here's the physics that makes slow fault motion terrifying. Every millimeter of plate movement that does not happen smoothly through continuous creep is instead stored as elastic energy in the crust. The fault locks, the plates keep trying to move, stress builds and builds and builds. Until one day the locked section can no longer hold the accumulated strain and it releases everything at once. The energy that builds up over years and decades in a locked segment of plate boundary is released in seconds. That instantaneous release of decades of stored elastic energy is what an earthquake is. And the longer a section stays locked while the plates keep pushing, the more energy accumulates and the larger the eventual earthquake will be. The northern edge of the western South Scotia Ridge is marked by a subvertical left lateral master fault. The plate boundary is segmented by a series of release zones that have favored the fragmentation and dispersion of crustal blocks across the region. Segmented means this is not one simple clean fault running in a straight line. It is a series of connected fault sections with bends, steps, and structural complexity that makes predicting exactly where and when energy release is very difficult. But that same complexity is also what makes the historical record here so important for understanding what is happening right now. The 2013 earthquake sequence along the South Scotia Ridge transform initiated with a magnitude 6.1 event on November 13th and a magnitude 6.8 event on November 16th, as foreshocks located roughly 50 kilometers west of the main shock. Then, on November 17th, the main shock ruptured with a magnitude 7.8. Read those numbers again. 6.1, then 6.8, then 7.8. The 2013 main shock did not arrive without warning. It was preceded by 2 foreshocks over 4 days that escalated in magnitude before the main fault rupture unleashed energy on a scale that shook seismographs worldwide. The 2013 magnitude 7.8 rupture spread primarily eastward at roughly 2.5 kilometers per second, with a total rupture duration of about 120 seconds. Aftershocks extended roughly 250 kilometers eastward, 120 seconds of rupturing. That is 2 full minutes of the ocean floor tearing apart. The rupture front racing eastward at 2.5 kilometers per second across a fault zone that ultimately generated aftershocks spread over 250 kilometers. The physical scale of what that 7.8 did to this plate boundary was enormous. Now compare that 2013 opening sequence to what just happened yesterday. The 2013 sequence started with a 6.1, then escalated to a 6.8, then exploded to a 7.8. Yesterday's sequence started with a 5.7 and escalated to a 6.2 just under 8 hours later. The epicenter of August 22nd's 6.2 is only 67 kilometers, which is 42 miles, from the 2013 magnitude 7.8 epicenter. The fault motion in yesterday's earthquake is pure left lateral strike slip, the exact same motion that characterizes every large historical earthquake on this boundary. The depth is shallow, matching the 2013 events. And the sequence shows the same escalating 2 earthquake pattern that preceded the 2013 catastrophe. None of this means a 7.8 is coming tomorrow. Let that be completely clear. Nobody can tell you that. Earthquake science does not work as a reliable short-term prediction tool, and anyone who tells you otherwise is overstating what the science can actually deliver. But what the historical record, the fault mechanics, the seismic behavior, and the location of yesterday's earthquakes altogether tell you is that this is not a random isolated tremor in a geologically quiet place. This is a very specific type of earthquake on a very specific fault, in the same section of that fault that has produced some of the most powerful strike-slip earthquakes in the southern hemisphere in the modern era. That combination demands serious attention. Let us go back even further in the historical record, because 2013 was not the first time this specific plate boundary demonstrated what it is capable of. The 2003 Scotia Sea earthquake of magnitude 7.6 demonstrated the potential for large seismic events within the system. This earthquake occurred along the South Scotia Ridge and was felt across much of the southern Atlantic region. So within a span of just 10 years, this same boundary produced a magnitude 7.6 in 2003 and a magnitude 7.8 in 2013. 2 major earthquakes approaching magnitude 8 on the same fault 10 years apart. And now in 2026, 13 years after the last major rupture, the boundary is producing an escalating 2 earthquake sequence in the same zone where both of those previous events originated. 13 years, that is important. Fault sections that have been locked since their last rupture have had 13 years to accumulate fresh elastic strain from the continuous plate motion. At 11 millimeters per year of plate movement, 13 years represents roughly 143 millimeters, about 5.6 inches, of total plate motion that either happened through gradual creep or was stored as locked elastic strain. If that section near yesterday's earthquake epicenter is partially locked, it has had over a decade to reload. Now, let us talk about the specific ground motion data from yesterday's magnitude 6.2, because the technical details of how the crust moved are extremely revealing. The moment tensor analysis of the 6.2 shows fault planes that are nearly perfectly vertical. Dip angles on both fault planes are in the high 80-degree range, meaning the fault surface is essentially straight up and down, nearly perpendicular to the Earth's surface. The rake values, which describe the direction of slip motion along the fault plane, are extremely close to pure horizontal. What this tells you is exactly what type of earthquake this was. The crust on one side of the fault slid sideways past the crust on the other side. It did not push up or pull down, it slid sideways. Pure left lateral strike slip motion on a nearly vertical fault plane. This is textbook South Scotia Ridge behavior. This is mechanically identical to the 2003 magnitude 7.6. This is mechanically identical to the 2013 magnitude 7.8. Such sideways moving events can destabilize adjacent segments of a fault in a sort of domino effect. The British Antarctic Survey published that assessment based on direct observation of what happens to this specific fault boundary after major strike slip events. When one section releases its stored energy, the stress does not disappear, it redistributes. Some of it goes into the surrounding crust as aftershocks, but some of it transfers to adjacent fault sections that were already under stress, effectively pushing them closer to their own breaking point. This is called stress transfer, and on a segmented fault system like the South Scotia Ridge, stress transfer from one section to its neighboring sections is a real mechanism that scientists have documented here specifically. Let us talk about what is physically near the epicenter of yesterday's earthquake, because the geography matters for understanding the human dimension of this story, even though the South Scotia Ridge is one of the most remote places on Earth. The Argentine research base Orcata Station, perched on Laurie Island since 1903, holds the distinction of being Antarctica's longest-running research facility. It maintains an unbroken scientific presence with around 14 people, weathering the winter months, and up to 45 researchers during peak summer operations. That research station has been continuously occupied for 123 years. It sits on Laurie Island, one of the 4 main South Orkney Islands, and the western edge of that island group is roughly 50 kilometers, about 30 miles, from yesterday's magnitude 6.2 epicenter. Seney Research Station on Seney Island serves as Britain's window into Antarctic life. The station's climate is characterized by low temperatures, gales, and coastal weather conditions. Researchers have been collecting microclimate records for over 25 years. Seney Island itself spans 6.5 kilometers in length and less than 5 kilometers in width, with Seney Research Station housing typically around 5 to 10 scientists during the summer season. These are real human beings conducting real scientific work less than 100 miles from where a magnitude 6.2 earthquake just struck. Not a large population, not a city, but researchers who have chosen to work in one of the most extreme environments on the planet and who are now sitting in the aftershock zone of a significant shallow earthquake on a fault that has produced near magnitude 8 events. Now, here's the broader regional context that makes the timing of yesterday's earthquake deeply significant. The South Scotia Ridge did not rupture in isolation from everything else happening in the South American tectonic system. Venezuela was struck by 2 powerful magnitude 7.2 and 7.5 earthquakes on June 24th of this year, causing extensive damage and thousands of deaths. On August 10th, a magnitude 7.4 earthquake struck the department of Chaco in Colombia, killing at least 329 people, injuring more than 4,600 others, and causing extensive damage across the country. And just 2 days ago, a powerful 7.2 magnitude earthquake struck southern Peru, Venezuela, Colombia, Peru, in a span of less than 2 months. And now the South Scotia Ridge boundary, which forms the southern tectonic boundary of the broader South American Plate system, is producing an escalating sequence at the very moment that seismicity has surged across the entire region. The geological connection between the South Scotia Ridge and the South American tectonic system is not abstract. The Scotia Plate formed when the Drake Passage opened, separating South America and Antarctica. It sits directly between these 2 enormous plates, with its boundaries wrapping from Tierra del Fuego around the Scotia Sea and toward the South Sandwich Arc. At the western end of the South Scotia Ridge, near the Drake Passage, the fault system transitions and connects to transform faults running through Tierra del Fuego and the southern tip of South America. The Magallanes-Fagnano fault system in Tierra del Fuego is part of the same broad left lateral plate boundary, accommodating sinistral motion between the Scotia and South American plates. It has its own history of major historical earthquakes, including a magnitude 7.8 in 1949. These systems are geologically linked. Scientists are careful in their language about whether earthquakes in one part of a system directly trigger earthquakes elsewhere. And that caution is scientifically justified because the distances involved in the physics of stress transfer are genuinely complex. Dynamic triggering, where seismic waves from one earthquake temporarily alter stress conditions on distant faults, is real and documented, but it operates over short timescales and relatively limited distances at the magnitudes being discussed. The more significant point is that the South Scotia Ridge does not need any external trigger to be dangerous. Its own internal stress accumulation from 13 years of locked plate motion is more than sufficient to explain significant seismicity. The regional context simply adds another layer to an already compelling picture. What are scientists specifically watching after yesterday's events? There are 3 things that will tell the story of whether this stays a moderate sequence or escalates towards something historically significant. The first is the spatial migration of aftershocks. Aftershocks from yesterday's 6.2 that stay tightly clustered around the initial epicenter suggest a contained rupture zone releasing local stress. But aftershocks that spread east or west along the South Scotia Ridge boundary indicate that the rupture redistributed stress to adjacent fault sections, and those sections are now responding. The direction and extent of any aftershock migration over the next 48 to 72 hours is the single most important indicator of what this sequence may become. The second thing to watch is the focal mechanisms of any subsequent events. Every earthquake that follows the initial sequence can be analyzed for its fault motion. If follow-on events show the same nearly vertical strike-slip mechanism seen in yesterday's 6.2, that confirms the sequence is confined to the South Scotia Ridge transform system and behaving consistently with its established seismic character. That is the expected result. But if any events show different fault geometries, it could indicate that the stress field is more complicated or that secondary structures near the South Orkney microcontinent are being activated. The third and most critical thing to watch is whether any future events in this sequence begin migrating toward the sections of the South Scotia Ridge that ruptured in 2003 and 2013. The 2013 main shock hypocenter was roughly 50 kilometers east of its foreshocks, and aftershocks extended 250 kilometers further eastward. Those sections of the fault absorbed enormous slip in 2013 and have been reloading since. Whether the section immediately adjacent to them, where yesterday's earthquake struck, transfers significant stress in their direction is the key question for anyone monitoring this boundary over the coming days. Let us also address something that will come up in comments about this video because it always does when the Scotia Sea makes news. There's a theory that circulates persistently and loudly, claiming that a major rupture near Antarctica will somehow connect to or trigger the Cascadia subduction zone along the Pacific Northwest coast of the United States. This is not how tectonics works. The Cascadia subduction zone sits on the opposite side of the planet from the South Scotia Ridge. The two systems are geologically distinct, mechanically separate, and connected by nothing more than the general fact that both sit on planet Earth. The seismic energy from a magnitude 7 or even an 8 on the South Scotia Ridge cannot travel through thousands of kilometers of ocean floor and load a subduction zone in the Pacific Northwest. The physics do not support it, and no credible seismological research has ever demonstrated a mechanism by which it could happen. What the Scotia Sea is genuinely dangerous for is its own immediate seismic environment and potentially its local tsunami generation potential, which in this case is minimized by the strike-slip fault motion. Strike-slip events, where the crust slides sideways, do not pose a significant tsunami risk. However, they can destabilize adjacent segments of a fault in a sort of domino effect. The 2013 magnitude 7.8, despite being one of the largest strike-slip earthquakes ever recorded in the southern hemisphere, did not generate a significant tsunami precisely because the fault motion was primarily horizontal rather than vertical. Any future large event on this same fault geometry would carry the same characteristic. Here is what you need to carry away from everything you have just heard. Yesterday's magnitude 6.2 is the largest earthquake globally in the past 24 hours, confirmed by multiple independent seismic agencies, including the USGS and EMSC. It struck at 10 kilometers depth on a fault that has produced magnitude 7.6 and magnitude 7.8 events within the last 23 years. It was preceded by a magnitude 5.7 just under 8 hours earlier, mirroring the escalating foreshock sequence that preceded the 2013 catastrophic rupture. Its epicenter is 67 kilometers from where the 2013 7.8 originated. Its fault motion is pure left lateral strike slip, mechanically identical to every prior major event on this boundary. And it is happening 13 years after the last major rupture, more than long enough for significant elastic strain to have reaccumulated in the surrounding fault sections. According to the USGS, there are no land-based observations within the Scotia Plate to measure plate motion. All reported plate motions are derived from remote earthquake recordings. That sentence is critically important. We know what this boundary is doing because of the earthquakes it produces. There are no GPS stations sitting on the Scotia Plate telling us how fast stress is building. There are no strain gauges. The only way we can measure what this boundary is doing is by watching the earthquakes it generates. And what the earthquakes it generated yesterday are telling us is that this boundary is active. It is rupturing in the same zone that has produced near magnitude 8 events before, and it is doing so with an escalating 2 earthquake sequence pattern that deserves every second of the attention it is now getting. The South Scotia Ridge is one of the most seismically powerful and least monitored tectonic boundaries on the planet. It sits between 2 enormous plates in the most remote ocean on Earth. Almost nobody lives near it. Almost nobody talks about it. And that obscurity is exactly why it keeps surprising people when it does what its history says it can do. Right now, the aftershock sequence from yesterday's events is developing. Scientists are watching the data stream in. The question of whether the August 22nd, 2026 sequence stops here or becomes the opening chapter of something larger will be answered by the data over the coming days. The South Scotia Ridge has earned the right to be taken seriously. Yesterday, it reminded the planet that it is still there, it is still moving, and it still has plenty of stored energy left to release.